This is lesson 8.3, Solving Right Triangles. Let's go ahead and open up in prayer. Father in heaven, thank you for another day. I thank you for the student you've given me. I pray, Father, that you would help me to explain the concepts in this lesson in a way that's understandable and retainable by my student. Give them the opportunity to study the material in this lesson. Give them good insight as they work through the problems, and help them to come to a place where they can master the concepts of this lesson so that they don't need anyone else to teach them about it, but they can actually use it. We thank you for Jesus and what he's done for us on the cross. Help us not to lose sight of that. In Christ's name, amen. Our objective today is we're actually going to use trigonometric ratios to find angle measures. That's different. In the previous lesson we found side measures. Now we're going to find angle measures in right triangles and to solve some real-world problems. Okay, so some roads are very, very steep, and because of this, highway engineers give a percentage measure to hills called a percent grade. For example, a 35% grade means that the hill rises 35 feet for every 100 feet of horizontal distance. So if you travel 100 feet horizontally, the hill will rise 35 feet. That's what a 35% grade means. Example 1, identifying angles from trigonometric ratios. Use the trigonometric ratio cosine of angle A equals 0.6 to determine which angle of the triangle is angle A. So here I've got angle 1 and I've got angle 2, and one of these angles is angle A. So we're going to use the definition of cosine. Cosine is defined to be the adjacent leg divided by the hypotenuse. So first I take the cosine of angle 1, 3.6 divided by 4.8, and I get 0.6, which is exactly what I want. I do the cosine of angle 2, and I have the ratio of 4.8 over 6, which is 0.8. Okay, what's my conclusion? Since the cosine of A is equal to the cosine of angle 1, we both got 0.6, I may conclude that angle 1 is congruent to angle A. Alright, go ahead and pause the video and try the following 1A and 1B on your own. In a previous lesson, we learned that the sine of 30 degrees was 0.5. Conversely, if you know that the sine of some angle A is 0.5, then you can know for certain that the measure of that angle is 30 degrees. Now, if you know the sine, cosine, or tangent of an acute angle measure, you can use what are called the inverse trigonometric functions to find the angle measure. And so these are the inverse trigonometric functions. If the sine of angle A equals x, then the inverse sine of x equals a. If the cosine of angle A equals x, then the inverse cosine of x equals a. If the tangent of angle A equals x, then the inverse tangent of x equals a. One quick note, this -1 here is not a power, and so when I say sine inverse of a, that is not equal to the reciprocal of sine. So don't get into the habit of thinking that this -1 is actually a power. It's not. It's just a symbol indicating the inverse of the sine, the cosine, and the tangent. So sine inverse of a is not equal to 1 divided by the sine of a. Example 2, calculating angle measures from trigonometric ratios. You're going to need to make sure that your calculator is in degree mode before you do this. Use your calculator to find each angle measure to the nearest degree. So cosine inverse of 0.5 is 60. I have a nice little application, so I'm going to go ahead and open up my TI application real quick. And if you have a TI-84 or a TI-83, then this will probably help you to be able to do that. So again, make sure that your calculator is in degree mode And that's exactly where mine is. Mine is in degree mode right now. Now the way that you access the cosine inverse is you do the second key and then you hit the cosine key. And right above the cosine key is cosine inverse. Type in 0.5 and there's my 60 degrees. So you're probably going to use the second key to access the inverse sine, the inverse cosine, and the inverse tangent. What is the inverse sine of 0.45? Well, it's 26.7436839.5 and a whole bunch of other numbers. But in this lesson, when we find the inverse sine or the inverse cosine or the inverse tangent, we're going to round to the nearest whole degree. So we're going to say that the sine inverse of 0.45 is approximately 27 degrees. The tan inverse of 3.2 is 72.64597536 and a bunch of other numbers. And this is closest to the whole number 73. So we say the tan inverse of 3.2 is approximately 73 degrees. All right, try the following on your own. Go ahead and pause the video and try 2A, 2B, and 2C. Using the measures you're given to find the unknown measures is known as solving a triangle. To solve a right triangle, you either must begin with two side lengths or one side length and an acute angle. Here's a quick fact. So here's a triangle ABC. C is the right angle, and the sides are N, M, and the hypotenuse is P. Now we know that the sum of the acute angle measures A and B is 90. So angle A plus angle B is 90 degrees. But we can also rewrite the sine of angle A, or the angle A, as the sine inverse of N over P, opposite over hypotenuse. And we can rewrite the measure of angle B as the cosine inverse of N over P. So it's also true that the sine inverse of N over P plus the cosine inverse of N over P is equal to 90 degrees. You see, what the inverse trig functions do is they take a ratio and they give you as an output an angle measure. That's what they do. Example 3, solving right triangles. Find the unknown measures, round to the nearest hundredth, and angle measures to the nearest degree. And I'm going to show you two methods. So let's look at method 1. Method 1 is going to use the Pythagorean theorem to find the hypotenuse. So AB squared plus CB squared equals AC squared. Substitute in the values you know. So AC squared is equal to 81.25. Use the square root property, and so AC is approximately 9.01. Now to find angle A, I'm going to use the inverse tangent of opposite over adjacent. So the inverse tangent of 5 divided by 7.5 is approximately 34 degrees. And now I use the complementary nature of the acute angles. So I take 90 minus 34 degrees, and that gives me 56 degrees. And now the triangle is solved because I know all of the sides and I know all of the angles. Okay, let's go ahead and use method 2. Method 2, I'm going to start by finding angle A right now. So the measure of angle A is the inverse tangent of opposite over adjacent, and that's approximately 34 degrees. Now I use the complementary nature of the angles, the acute angles. 90 minus 34 is 56, so now I know angle C. Now I know that the sine of angle A over 1 is equal to opposite over hypotenuse, 5 over AC. I cross multiply. So AC is equal to 5 divided by the sine of angle A. But what is angle A? Angle A, by definition, is the tan inverse of 5 divided by 7.5. And so let me show you how you can calculate that right in the calculator right now. Let me clear this out. And so what we have here is we have 5 divided by the sine of the tangent inverse of 5 divided by 7.5. Now let's close the tan inverse and let's close the sine. And I get 9.01. And that's the hypotenuse, 9.01. All right, go ahead and pause the video and try the following problem on your own. Rounding too soon can really make a difference. If you use the Pythagorean theorem and round to the hundredths place in this picture, you're going to get about 15.62. But if you solve it this way, the measure of angle A is the inverse tangent of 10 over 12, and that's approximately 40 degrees. The sine of 40 degrees over 1 is equal to 10 over AC, opposite over hypotenuse. Cross multiply, AC is 10 divided by sine of 40, which is 15.56. So the two answers that we just found have a difference of 0.06. So the moral of the story is, don't round too soon. If you round too soon, you're going to get errors, small errors, but errors nonetheless in your answers. Example 4, solving a right triangle in the coordinate plane. The coordinates of the vertices of triangle JKL are, J is negative 1, 2, K is negative 1, negative 3, L is 3, negative 3. Find the side lengths to the nearest hundredth and the angle measures to the nearest degree. Now because JK and KL are both vertical and horizontal respectively, JK is just 5 and KL is just 4. But JL, you have to use the distance formula to find JL. And so we plug in the values from J and L and we get approximately 6.40. We know that angle K is 90 degrees. So we start with the measure of angle L, and that will be the tan inverse of the opposite side divided by the adjacent side, and that's approximately 51 degrees. Now we use the complementary nature of the acute angles. 90 minus 51 is 39, so angle J is 39. And now the triangle is solved because we know all of the sides and we know all of the angles. All right, go ahead and pause the video again and try the following example on your own. Example 5, travel application. There is a hill in San Francisco with a street named Lombard Street. This hill is said to have an 84% grade. Now remember, the problem is the hill has the grade of 84%. Lombard Street, they actually have created 8 little sideways turnabouts so that people can actually get up this hill. So the grade of the street is different from the grade of the hill. So we're just looking at the hill. Question: what angle does the hill make with a horizontal line? First thing is to remember what 84% grade means. It means that for every 100 feet you travel horizontally, the hill rises 84 feet. So, knowing that, we know that 84 is the opposite and 100 is the adjacent, and that means we're going to use the tan inverse of 84 over 100, and that gives us approximately 40 degrees. Go ahead and pause the video and try the following on your own. And that is Lesson 8.3, Solving Right Triangles. God bless you, wherever you are today.